Hello, everyone. Well, it was the first time the actual sound played, so that could be a good sign for me presenting here today to you. All right, so I have a little note here so I don't forget everything that I wanted to say in the beginning of the presentation. And before I get into the presentation, first of all, I would like to thank Farfetch, who invited us and myself to be here and talk a little bit about big data, which is my area of expertise. And second of all, so who think they know the answer to this question? Anyone? Who goes for yes? Is it Hadoop and big data one and the same? Okay, so who thinks it's not one and the same thing? Okay, so most of the people think I believe the right way, and so probably I don't have to say anything else because everybody kind of know the answer. Well, this is just a topic to discuss a little bit about these topics within itself. So, a little bit about myself. So my name is Nuno Barreto. I am responsible within XpandIT for a unit that is focused mainly on big data technologies. We'll discuss a little bit about what big data technologies kind of imply. And in terms of my background, I'm contrary to most of you, I'm not a developer. I did some development, but I kind of picture myself more as a DevOps kind of person and more on the infrastructure side than a developer, all right? So I think it will explain why I got into the big data the way I see it. Okay, so a little bit about XpandIT. I don't know if anyone knows the company. We started in 2003, so 11 years ago, or actually 12 years ago. We started just doing EAI, very small company, and with time we kind of grew, started working worldwide in a lot of different projects. 2008, we kind of started diversifying our skills, and we kind of built areas for BI, Enterprise 2.0, and other stuff. One of the major milestones that we got was in 2009, we built a nearshore development center very close to Porto, so in Viana do Castelo, so we have a development team there. And finally, in 2014, after doing a lot of work in big data without having a specialized unit, but we did a lot of work around it, mostly in international projects, in the BI areas, we kind of started officially a big data unit. So in terms of the agenda today, when I was thinking about, so what should I talk about in this kind of event? And it's not easy because we didn't know exactly like who's going to show up. And yeah, well, I had the idea that a lot of developers would come here, but I also know that most of the people are not working within these areas. So who think they have a very good definition for big data? Anyone? But for sure, most of you have heard a lot of definitions for big data, and probably most of all are very, not very precise, to say the least. So I'm going to try to explain at least my view on big data and explain to you what it means to me. And again, bringing the subject about what could I talk about that could be interesting. So I didn't want to go too technical because I may lose some people, but I didn't want to be like too on the surface because it turns out not to be interested. So I hope I get a good balance between these two kind of speeds. So in terms of the agenda, so yeah, so talk a little bit about definition of big data and how we define it. Talking about Hadoop, so does anyone knows Hadoop? Okay, a few people, good. And explain why it's the data platform and not database as such. And then discuss a little bit about use cases and use cases that are not, I would say, the most traditional ones on Hadoop, okay? So this is the basic, you have seen very many versions today of this slide about the new ways and like there are so many data sources. And yeah, well, that's true. But most of you are not working on these new data sources. Most of you are working on the traditional data sources, the structured data, and we'll get there. Nonetheless, yes, there's a potential to work with a lot of different data. But there are still cases where with the traditional data, we need big data technology. So this is another definition that we see a lot, and the problem with this definition is that it's very imprecise, right? So it's about volume, but what? Terabytes, petabytes? What volume makes it big data, right? Hard to tell. I don't have an answer for that, by the way. So is it variety? Right? Is usually not very much considered, but I think it's a very important kind of item in big data, in considering something big data. But anyway, so variety. We have a variety of information, and it's very kind of abstract saying that variety is an issue. And then velocity. Well, we'll get to velocity. Okay, so why is volume an issue these days? So when we're talking about structured data, we're talking probably about customer interaction. So if you think of a bank, right? So a bank kind of stores transactions, actual transactions that a customer did, a payment, transfer, whatever. So that's a customer interaction. But imagine, sorry, actually that's a business transaction. The customer interaction, for a customer to do that, imagine on a home banking portal, how many interactions he does. He logs in, he goes to a menu, he selects whatever, he chooses how much he needs for the amount for the transfer to be a destination. He clicks, there's a validation of a token of some sort. So there are a lot of customer interactions to support one business transaction. And before, we were used to kind of store only the business transaction and not the customer interaction. There's a lot of value around the customer interaction to understand better the customer. The other side of this is that we produce a lot of data, and we only store a little bit. One of the most kind of interesting or important topics about the raw data is that people don't really think it's valuable, right? And maybe it's not, but maybe it is, right? So, and if we can get a way to store that data in a cheap way, then it at least unlocks the possibilities of exploring that data. So then about velocity, I talk a lot. I said velocity, we'll talk about it. In truth, velocity is most of the times a problem of money, right? If you have a database and it's slow, and you usually have it on SAS drives, not to get too technical, you can switch to flash drives, and then it's faster. It always comes to the cost of money. And if something is slow, you can put faster processors. Faster processors means more money, right? So latency, for the most part, is still a money problem. So a lot of these technologies, what they solve is throughput and volume, okay? Sure, they handle velocity in a certain way because they kind of lighten up the things they do, like transactions and stuff like that, to make it faster. But for the most part, all the big data technologies are answering throughput and volume issues, okay? I'm not undermining velocity and latency. I'm just saying that for the most part, it's still a money issue. All right, so back to data. That's another thing that I think it's still a problem. Like people don't understand really what data means when we divide it between structured, unstructured, and semi-structured data. And the other problem is that I usually see a weird kind of connect between, oh, big data is for semi-structured or unstructured data. First of all, well, that's true, but it's not only for that. And the reason is, yeah, so unstructured data. So if you look at that, we tend to generate, so unstructured data, it's larger than semi-structured data, which is usually larger than structured data. And usually we're not keeping a lot of unstructured data, and probably now more we kind of store more of the semi-structured data. And the thing is, in terms of definition of this stuff, like what's the use for unstructured data? Not much if there's no structure around the data. Sure, so what's unstructured data? It's like a movie or it's like a media file, whatever. Yeah, you can do some stuff on this. You can kind of find patterns and whatever. But these are things that are still a bit in the future. So if you want just a data repository for large files, yeah, well, you can use big data, but that's not where the value is. Semi-structured data, which is basically log files or you can kind of understand those as log files. Well, they have some structure within a log file, within a line of log. When you see it like that, there's no structure. But when you parse it, then you have structure there. And a lot of the work that we do with these platforms is to make that semi-structured data into structured data, right? So in the end, you need to get some structure into the data so you can analyze it, right? So it's the path and the road towards getting that structure that gives you the value of the big data. So what is there in the world for big data? And probably most of you would consider all those in the left big data, at least associate those technologies with the big data paradigm. And yeah, sure, but Hadoop is one thing, and we'll get there. Then there's NoSQL. NoSQL is a class, that's how I define them. It's a class of data engines that have something in common with Hadoop, but are basically targeting specific use cases. And there are some that are more adequate to one use cases, and some are more adequate to others, and there are some that are very, very, very flexible. On the right-hand side, you see some brands that some of you may not even know what they are. They are proprietary systems in some cases, like Teradata and Vertica, but they are big data, and you understand why I say that they are big data. Before that, so one of the trends, most interesting trends within this space, so it's Hadoop and MongoDB. I don't know if any of you went to the talk downstairs of Norberto, and he probably explained a little bit of NoSQL and MongoDB in particular. But anyway, so around these technologies, there's a big trend, there's a growing trend. Even when you compare this with NoSQL, so the search for the words Hadoop and MongoDB are very popular. So there's a big trend here. So what do they all have in common? And that's how I define big data technologies. They are all distributed, scale-out technologies. I think that's a very good way to define something. And remember that I told you that I'm the infrastructure kind of background type. And for me, this is very easy to understand. This is why I got hooked into this type of technologies. When I was kind of designing infrastructure, and every time we had a database, the relational database, it's really hard to scale. So you can only scale a database by putting more hardware or use some kind of technologies that end up being a bit of big data. So any of you know Exadata from Oracle? Exadata machine? Okay, so the Exadata machine actually, although it's an RDBMS, uses some of the principles of big data, right? So the storage cells, which is something inside Exadata, are a distributed way to handle queries, right? So it's a bit of big data. But then it still handles transactions, and it still handles referential integrity, and that's a problem for scale. So all of these systems usually don't support this by default. Or you can support this by losing some of the features that you have with these technologies. Okay, so let's kind of, at least for this talk, kind of agree on this definition, that a big data technology is something that scales out by adding new nodes, right? Okay, so Hadoop. How can Hadoop help? So Hadoop certainly is a scale-out technology in that sense, and for me, it's obviously a big data technology. And you see, I didn't give you any kind of definition of volume, variety, or velocity. I'm just saying that it's a scale-out technology. So when do you need a scale-out technology? When you need to handle a lot of volume and you need to scale out. You can scale up, but you're going to spend more money. So it's more efficient to use a scale-out approach. So again, that's the definition I have. So Hadoop can help. Yeah, certainly. But Hadoop is not a database, so it doesn't compare with a relational database management system that we have, the Oracles, the MySQL, the SQL servers, right? So it doesn't compare with that. So Hadoop is more of a data platform. And this is where it gets interesting, comparing Hadoop as an ecosystem with, for instance, MongoDB, right? So MongoDB is actually a database, right? But it's a NoSQL database, so it's still big data technology because it scales out, but you can use it in a lot of different use cases, right? So with Hadoop, you have an ecosystem where you can do a lot of different stuff. And actually, when you look at the slides from Cloudera Enterprise Data Hub, it's like one of the distributions of Hadoop, there's the file system, and oh, there's another NoSQL database. Yeah, so it's not a database. Within the ecosystem of Hadoop, there's a NoSQL database. Actually, there are more than one. Currently, Cloudera kind of ships the Data Hub with 2 NoSQL databases. One of them is HBase, which was on the previous slide, and Accumulo, it's another NoSQL database. But then on top of this, you can build a lot of different functions, right? So you have the traditional batch processing. You have analytical SQL. Whoa, we can do SQL with Hadoop? That kind of hints for structure, right? And that's not something we usually associate with Hadoop or big data, for the most part. Then there's a search engine here. Wow. There's machine learning, stream processing. Stream processing kind of sounds like real time. And usually people associate Hadoop in particular with a slow, like workhorse, right? The symbol, it's an elephant, right? An elephant doesn't run fast. To do stream, you probably need something fast. So maybe Hadoop these days is not so much of the elephant, it's much more of the ecosystem with a lot of different tools to handle a lot of different use cases. So one of the principles, and this is not exclusive to Hadoop, is the idea of not moving data to the compute. It's having everything together. So the idea of distributing stuff, it's important because you then can parallelize your processing and kind of subdivide it with the chunks of data you have close to the processors you have. So the data locality, and someone earlier kind of mentioned the importance of that in a totally different kind of subject, but it's true. One of the weakest kind of things that we have in the compute environment is the network. Either it's very expensive at the cost of money, so low latency is very expensive to achieve in a network. So if you can get your data close to your compute and kind of distribute the compute, then you're good. Again, so this is the principle, right? So the principle of distributing data across certain compute nodes and avoiding as much as possible, and this totally depends on the actual workload, but totally kind of distributing the load through the different nodes and having the nodes using their own compute, their own storage areas to kind of get the data. A very simple example of this that I think kind of resonates with everybody. So if you do something like a select count from a table using this principle, no matter how big the table is, you can always keep that select count to the desired latency as an operation, right? At least to a certain level. Because if your data doubles, then you can double the number of nodes you have, and because you're distributing the select counts on all the nodes, each node will only take care of the data within its node. So the time of the total operation remains constant, right? So it's very important. You cannot do this with a relational database, okay? And this applies to a lot of different kind of workload types. Okay, so in big data, what matters? Is this a technology or it's a use case issue? And yeah, well, we have the tools, and that's something that kind of, it's the industry, right? The industry came up with this idea of big data, right? Because it's probably easy to sell, and now it got a total mess because no one really knows what it means. Organizations and like high-level functions want to do big data, but what's big data? I mean, if I'm defining big data as a technology, so what matters? Is it the use case or the technology? And for me, certainly the most important thing is the use case. And the truth is that there are a lot of use cases that are only implemented or that are only able to implement, you are only able to implement those use cases if using big data technology, or at least the most efficient way from an economical standpoint to implement those use cases is by using big data technology, being Hadoop, MongoDB, or even other NoSQL databases. So the two kind of topics I wanted to talk about in terms of use cases are those two that I don't think that people usually associate with Hadoop in particular, which is structured data and streaming, right? So let's look at structured data. This is just a relational kind of scheme, right? Everybody has seen something like this. So how do you do this in the big data environment? Can you do this? Sure. A table is just a file within an Hadoop namespace. And you build metadata on top of that to say that a file is composed of, or includes all the data within a certain directory. And each line of that file has a certain structure. And then I can read the file in parallel and kind of work on that data really fast. What I don't have, though, is referential integrity. Sure, that's not a problem for most of the use cases. This could be another interesting topic for a different talk, and actually very adequate to talk in the sense of MongoDB. That's a different kind of subject. So a relational model, if you take the connections, which, by the way, you can kind of sometimes do that in a relational database management system because the referential integrity comes at the cost of performance. Every time you do an insert in a table, you need to be verified against the constraints that it has. So sometimes people, for performance reason, even by using relational database, they kind of turn off the constraints, right? Because you just have to. Anyway, so I was saying, if you take the connections out, those could be just files, right? And if you can have metadata on top of it, just saying which columns you have and what the type of columns you have, then you can do joins. Joins is just a matter of ordering a column, ordering another column, and kind of mashing up the data, right? So that's basically it. Within Hadoop space and with the ecosystem, there are a number of ways to do SQL. One of the most traditional ways is Hive. Hive is, and it's true, it's very slow because it's just a preprocessor for MapReduce, and I'm not going to talk about MapReduce. But it's slow, and it's usually people associate the slowness to Hadoop because of this, because they think the only way to run SQL is by using Hive. Not true. There are two things, more recent. So Impala on the left-hand side is just an MPP engine that you can use on top of HDFS files. And I encourage you to try this and see how fast it is. You can have an interactive experience just by doing SQL. It's nothing like using Hive. And you can even build dashboards on top of this. Not very high consumption dashboards. But anyway, so it's very interactive. So it kind of solves one of the problems of Hive. And still there's a lot of different streams in terms of this idea of ecosystem. So yeah, there's Impala, which is basically developed by Cloudera. But there's also Spark. And within Spark, which is another component, there's also a SQL engine. So now there are people doing Hive with Spark, using Spark as the execution engine for the Hive QL, which is basically a SQL language. So there are a lot of kind of options here. And it goes like this, right? So batch MapReduce, that old idea of Hadoop. And by the way, Hadoop has more than 10 years of age. So it definitely had to evolve during time. Then doing remote queries, the problem is the problem of the data movement, right? You have to bring the data, and that means network traffic, and it takes a long time. So one option is definitely Impala, right? So to do this SQL processing. And this is basically a kind of design of a traditional, not traditional, like the new way to do EDW, right? So enterprise data warehouse. You can just have a scale-out distributed database where you kind of massage all your data and process all your data at the cheap cost, and you kind of load that data already aggregated to what you need into your EDW. And EDW starts being what it should be always, which is just a repository for aggregated data to be used and consumed by dashboards and reports, right? And not to massage data. It's not, the idea of the data warehouse was never to kind of be a way to kind of process data and do ETL on it. So the other use case that, again, it's not usually related with Hadoop is doing real-time stuff. And there are these two components within the Hadoop ecosystem that are very powerful combination. And I'm pretty sure that even though Spark is 2 years of age, I think, 2.5 maybe, and Kafka, it's even more recent, this is a very powerful combination. And this is basically what these two components do. So one of them, so Kafka, it's just a queue, right? So everybody knows JMS queues and stuff like that, right? It's just a queue. So the good thing about this queue is that it runs on top of Hadoop. It's just another component. And because it runs on top of Hadoop, it becomes elastic, right? So it can grow as the cluster grows. And if you need, it's just kind of easy to kind of add one node and just extend your Kafka cluster. And it has all these features. So it's low latency, if the hardware allows for it, but it's in memory, so everything works in memory. It can be persisted to the HDFS, so it's fault tolerant because it runs in a cluster. It's a very powerful kind of component. And then on the other hand, you have Spark. Spark is becoming, or will, at least in my opinion, will replace MapReduce and maybe a lot of SQL engines that are out there because it's basically a programming framework where you can, at the same time, do batch, do real time, do streaming within the same space. So it's very, very, very powerful. And why are these two things, when they work together, when you put them working together, very powerful? Because the only way, well, that I know, to do real time, it's kind of to have whatever events you have, like writing somewhere, and somewhere is definitely a queue. And the problem in using queues, some queues are that they not scale very well. So if you do Kafka, so it scales really good. So you have your data streamed towards Kafka, and it solves the problem of buffering, right? So it's a queue, it's very fast, and it buffers your data. Even if you're not reading the data on the other end very fast for some reason, at least you have a buffer and the system doesn't stop. I can tell you that I know of cases of important infrastructures for banks in this country that kind of stall when they're logging because they're using a relational database as the backend for their logging system. And it stalls. So the entire kind of system stalls because everybody's like logging to the same place and it's a relational database. It could be solved even if they want to use a relational database just by putting a queue there, right? Just to absorb the impact. So one thing is putting that into the queue. And the other thing is reading from the queue. So Spark has a very kind of interesting abstraction within it, which is Spark streaming, which is just basically a higher level abstraction that takes care of the parallelization of this process that kind of connects to Kafka, and you can, in parallel, read Kafka stuff. And the good thing about this is that you can basically have, as soon as you create the data, an entire pipeline of data processing that scales elastically, all right? So as soon as you generate data, you put it into Kafka. And if you want to do different stuff with that data, let's say real time, you stream that data and do whatever. You can even kind of stream that stuff into MongoDB or HBase or whatever. But if you want to do batch with that, you can kind of write that into an HDFS file system and do your batch later. But it's a very powerful abstraction. I can tell you that in probably 2 to 3 years' time, everybody will be touching this type of components. If not now, you will, for sure. So just to wrap this up. So Hadoop, it doesn't solve all the cases. There are, and it's not the intent. There are other NoSQL databases that are very good for certain purposes that also have these features of scale out, right, that are very powerful in terms of growth. But Hadoop is definitely a very complex and strong ecosystem that can be used for a lot of different use cases. And it's good for structured data as well, right? So Keynote, structured data. The other thing is that SQL language is something that everybody knows, so it's a very powerful abstraction, and wow, you can use it against Hadoop. And it's not only even on just by using Hive, which is slow. You can use Impala, which is a very fast engine that connects directly to the data. So that's two. The other thing is you can do both batch and real-time stuff. So you can basically assemble a Lambda architecture built for both real-time and batch based on these components. And finally, this is technology, right? But you need to have the use case, okay? So, and that's basically it. I'd like to thank you for your time. I think I'm pretty much on target with the time, so 30 minutes. And thank you very much, okay? If you have any questions, just grab me around.